so here we go. When we see the word Riemann, what do we think of? Rectangle. So Riemann rectangle. And that means we're going to use area equals base times height. Now, I know some of you have been saying length times width, which is fine. It's the same thing. But I'm going to show you in a minute why really, if you stick with base times height, things get a little bit more consistent for you, but it really doesn't matter either way. Okay, so we are going to draw some function like this, whatever. Okay, the function itself doesn't really matter, so just some sort of something that's not just a straight line. All right, so we've been estimating using rectangles. Left-hand rectangles, right-hand rectangles, midpoint rectangles. We even did some trapezoids, right? So we can call it a left Riemann sum, right Riemann sum, midpoint Riemann sum, but you do not call it a trapezoidal Riemann sum, even though that's what the note said yesterday, because Riemann means rectangle. It's still it's a trapezoidal sum. You just don't put the word Riemann in there. Same concept and everything, but yeah. And Riemann is somebody's last name, but it also means rectangle. So, all right. So to estimate the area bounded by the graph, so this is our f of x. I feel like these lights is flashing. Either that or is it flashing or is it just me? Okay. Well, mine's not. Is it the projector bulb or is it one of these? I think it's the projector bulb. It's new. Is it a projector? All right. So anyway, to estimate the area bounded by the graph and the x-axis between the vertical lines x equals a and x equals b. So we're going to say here, this is going to be a, and we'll just put b down here somewhere. Okay. So we want to estimate the area under that curve, right? And we divide it into subintervals, which we'll get to in just a minute. Yesterday we drew rectangles with the height at the left endpoint, right endpoint, midpoint. Today we'll draw rectangles at some general point within the subinterval, not necessarily at the left endpoint or the right endpoint. So if I have, let's say that this is going to be the height right here. So our rectangle could maybe be like this. So it's not necessarily in the midpoint, and it's not necessarily, and it's not on the ends, is what I'm trying to say. But that's the height of my rectangle. So this is C1, which is like our little height. So this right here, which is the base of my triangle, remember is just a change in x. So this is a delta x sub 1. All right? Does that make sense? Then I'm going to draw another another rectangle. We'll make this the height. This can be C2. Oh, well, that would make sense there. And mine, no matter what I do, they always kind of look like they're in the middle, not what I'm trying to do. So this is delta x sub 2. Well, it could be in the middle, but the idea of this is, and I didn't even draw that one right. I was trying to draw that as the height, but I was making it a left-hand rectangle without needing to. It should look more like that. Trying to make this the height and this the height. Sorry. Which it could be in the middle, but what this is saying is that this isn't particularly a left hand, a right hand, or a midpoint rectangle. It's just some random point that is the height there. So I'll do this one a little bit closer so we can make it look a little bit more obvious. Maybe like that, so where it really looks like it's not in the middle. So this point right here, this would be C3, and this would be delta x sub 3. So then I'm going to do a dot, 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 meaning there's other rectangles in between there maybe. And then we can have this one, and it go this. So this isn't necessarily C4 because we had C4 and something else in there. This is going to be C sub K, and that's a sub, but my sub K, like the sub 1, 2, and 3. So that makes this delta x sub K, and K is just some value. That could be the 5th, the 6th, the 7th, whatever. Then we can keep on going, a little ellipses here, and then we're going to have another rectangle here, where this would be C sub n, because it's going to be the last one. It'd be how many total we have. And then this whole thing here is, or I'm sorry, that interval is delta x sub n. So that way we don't have like a specific one with a specific amount of rectangles. This could kind of be anything. So the base of each triangle, or the width of each triangle, is our change in x, right? The height of each rectangle, I think I just said triangle, the height of each rectangle is the y value. Does that make sense? Right? Change in x times the y value. That's what's happening there. Right? And we're finding the area, and when you see Riemann sums and you see integrals, you do want to think area, but you need to think of it as an area concept, not necessarily as area as you've always been comfortable with area. And I'll explain that a little more as we get through it. But so this is what we have here. So we still have rectangles. Hopefully I won't say triangles again. We still have rectangles, but they're not left, right, or midpoint. So we have some general point sub-interval, not necessarily at the left endpoint, right endpoint, or at the midpoint interval. So we're going to let x equal c sub k. So this x value here, that's our c sub k. It's some random value that we have. Okay? That's going to determine the height. That c sub k, whatever that value is, let's say that's at 12. That's not the base. That's not the height. That's the x value that we use to find the height. Does that make sense? So if I find the y value at this x value, that gives me the height of the rectangle. That's what I'm looking for here. So it says it's any point in the kth subinterval. So this is my kth subinterval there. So we drew each rectangle with the height of f of c sub k. Because this is c sub k right here. This, so my ordered pair right here would be c sub k, comma, f of c sub k. It does look like Chick-fil-A. It's better than what I thought you'd think it looks like, so. I mean, yeah, it's hard to not see it, I know. Just don't say it, we can see it. All right, so we have this x, this is our x value, this is our y value. So does that make sense? Because you'll see this notation. All that means is we are about, this is our x value, y value. The y value is what gives us the height, right? The delta x is what gives us the base, right? So the area of our rectangle, and even though we write base times height, and I think because of what we're using, and we usually put dx at the end, we're actually going to write this area more as height times base, but that's the same thing, right? I mean, it's base times height, height times base, it doesn't matter. So your area of a rectangle is going to be f of c sub k. That just means your y value times your change in x, delta x, sub k. And when we generalize things, they start to look a little bit more difficult or confusing. It's really still just base times height, but it looks dirty. Right? Okay, maybe you'll remember it. If it looks. But we have the height times the base. We all good with that? That's for one of them. If we want all of the rectangles, we're going to have to add them all up. Do you remember? My feelings are going to be really hurt if you don't, because it's hard to. Do you remember the symbol for summing something up? Yes, sigma, good. So it's the sigma. So we're going to sum it up because we're going to sum up all of the areas, right? So we're going to sum up the areas of all of the triangles, f of c sub k times delta x sub k. And then k is going to equal, it's going to go from 1 to n, whatever it happens to be. That's why it's called a Riemann sum. We're summing something up. Right? What? It's called a Riemann sum. I know. And this is why freshmen don't take calculus. No, I'm just kidding. Well, this is why I would never teach calculus to freshmen. One of the reasons. All right, so are we all good? Because I don't want to confuse you by generalizing things, but this is what's happening. So what we want, so we've been approximating, right? We did a lot of approximations yesterday. Some were better than others. Some were overestimates, underestimates. In a situation like this, we can't really tell. And what you want to keep in mind, and one of the reasons besides time, which Ms. Bruce talked about yesterday, that you don't always want to have to draw your picture if you're actually approximating with Riemann sums, is that if you have a question about is it an overestimate or underestimate, you can't really go by looking. Because first of all, you drew the picture, right? And it's probably not super duper on the spot accurate. You don't really have enough information. So you have to be careful, you know, making those decisions. Some of them are obvious. Some of them, like here, who knows? Because, you know, we didn't even draw all the rectangles. But what do you think we could do so that we could get what could make our area under the curve better and better, and what could help us get an exact area? What are you thinking? I'm going to let you think for a second. I had to restart my computer. I just realized I forgot to put something up there. So, forgot to reopen something. Speak among, well, not a formula, just a concept. Because, like, I mean, we just kind of have a concept here. What could we do differently? We kind of still do the same thing, but how can we make what we're doing better to give us a, better, more accurate answer? Multiply all the subintervals. Okay, I don't know what the heck is happening over there now. Sorry. What do you mean by multiply all of the subintervals? Okay. Mm-hmm. Right. Okay. Okay, so that is true. So you're saying basically make sure we include all these rectangles in here? Yes. Okay, and I would agree with that, right? Because if we just do what we see, that's not enough. So we have to include the ones we even don't see, and that would give us a better one, right? What would make that even better? I mean, you're on the right track. It would make it better. Okay, subtract the negative spaces and that, so we'd have to figure out what those are, right? And just finding this area, we don't have a formula for this weird shape. We don't really have formulas for these weird shapes either, so that'd be a complicated thing too. That would work. Like subtract this and add this, right? What would help us have less of that to add and subtract? Possible. Well, I can give you the equation of the line. Sometimes you will have that. Not this one because I just made it up and it's a squiggle. If I didn't use a rectangle, okay, what could I use instead? A trapezoid? Okay. So do you think if we did that, the trapezoids would be better? On most of what we did, they looked better, right? And that would get us better, okay? So that gets us better and better. And so we're working towards how can we get the exact area? Yes, find the integral. Back up a little bit. Cheater. How could we with our rectangles? No, you don't get to change the function. I'm sorry. Any ideas? What can we do with our rectangles besides change them to trapezoids, which is not a bad idea, but let's stick with rectangles because we don't want to upset Mr. Riemann here. Well, if we slant them, they're not rectangles. What do you mean by slant them? Okay, so if I did that, then I'm going to have blank space under here, right? What if we did what? Smaller rectangles. Do you think smaller rectangles would help? If these rectangles were skinnier, would I have less of this space and this space? And then skinnier and skinnier, right? Have more subintervals, right? Okay, so you're on the right track. You're all kind of you were thinking good. So let's look at this. Let's use, That's just some function. Don't worry about what it is. It's just some function, just like the squiggle I drew. So let's look at left rectangles. Okay? And so here we have one rectangle. Okay? Then I'm going to move that to, now I have two rectangles. So is that better than when I just had one? We're not real sure, right? Because it's weird, right? Okay. All right, so then there's 3. Is that better? It's better. It's still not, it's not good, but it's better. 4, let's just let it go. Make it skinnier and skinnier. So how do you think, so then how many though? Infinite. What do you think of that? Here I was going up by 1, let's start going up by 10s. Basically. But notice how the more and more we get, oh, it starts over. But I don't know how far it went. I wasn't really paying attention. But yeah, more subintervals, exactly. And how many? An infinite amount. Okay, so we need to sum up an infinite amount of rectangles. Now, we didn't have a problem summing up 3 or 4 or 5 yesterday. How long is an infinite going to take you? Forever? Exactly, forever. All right, it's going to take you forever. And so, let's see. I don't know how to stop this. So our answer here is just going to be use an infinite number of rectangles. So you've got 2 options here on how that works. We're either going to let n, because we just, up above, we just knew it was n amount. We didn't even know how many, if it was 10, 20, 30. We let n approach infinity, or delta k, delta x sub k approach 0. So an infinite number of rectangles also means we want the width or the base of those rectangles to approach 0. Where basically you have, I wish I had one, I don't have one. You know those little, I don't know if I guess you'd call them toys, but they're usually rectangular and they look like they have little nails. You can put your hand up in there, yeah. So kind of like that, picture one of those going up underneath the curve, right? And the skinnier and skinnier they are, the more it's going to fill in, right? So we have to have an infinite amount of them, almost like they're just little lines that don't have any width. Well, how do you find the area of that? Well, you really can't, right? So that's where your definite integral comes in, right? So the notation looks crazy. It's not going to be as bad as what it may look like right now. So this is called an integral, boom, like this, right? So this is the little integral symbol. It's like a tall S, kind of like that. It goes from A to B, so we always read it from bottom to top, just like we did on a sum, okay? So it's we're integrating from A to B, which means we're finding the area under the curve between A and B on the graph of the function dx. Means we had something and we took the derivative of it, right? Dx, doesn't that come from your derivatives? That's equal to the limit of the sum, like we just talked about, where n approaches infinity. Or, same thing, and we take the limit as delta x sub k approaches 0. They're the same things either way. So it's still all tied to the limits, okay? We're not done with limits. Limits is tied to like everything, okay? So that's your definite integral. Definition. Couple of things that are important here. For f of x, which is continuous on the closed interval a to b, okay? So it has to be continuous. We're not using any piecewise functions here. The definite integral of f from a to b is the limit of the left or right-hand sums within subdivisions as n approaches infinity. So it really doesn't matter if it's left or right if n's going to approach infinity, because they end up being the same in the very end anyway, right? It's just kind of how you get there if you're coming from the left or the right. And so this is how we write it. Integral from a to b of f of x dx. So terminology here. F of x is the integrand. It's what we're integrating. A and b are the limits of integration. Dx is the variable of integration, right? It's just the change in x. That's all it is. Okay? All that good so far? All right. So when we start this straight from area, and visually more so than anything. So it says that this means that for many questions, we are able to calculate the definite integral by using simple geometric formulas. But they're only simple if you actually know them, people. You got to know them. These are the ones you absolutely have to know. Okay? You have to know the area of a rectangle. Area of a rectangle, and again, length times width is okay, but we're going to use base times height. Okay? You also have to know, so rectangles, you have to know triangles. What's the area of a triangle? 1/2 base times height. See, they're all kind of, because triangles like half a rectangle, right? Okay? Then the area of a trapezoid, remember, what do we think of, what do we relate it to? There you go. So we have 1/2, which means when we cut its head off, we have 2 bases, right? So base 1 plus base 2 times the height. And then circle. Area of a circle, pi r squared. Good. Here's a little side note. What's the circumference of a circle? 2 pi r. Now that you're in calculus, what do you notice?
It's derivative.
Yep. Yeah. So now maybe you can, hopefully remember them correctly, that you area and you take derivative, you get circumference, and there you go. So you need to know circumference formula also, but we're doing area right now, so I am going to mark it out just because I don't want you to accidentally use it for something. But I just wanted you to see that. Okay, so we're going to sketch draw a sketch of the graph. So sketch means like it can be icky, like this over here. It doesn't have to be beautiful, but it needs to be decent enough for you to be able to do something with it. Evaluate the different interval. Okay, so we are integrating from -6 to 3 this function dx, right? So let's draw a little. All right, so we need, we're going from -6 to 3. Okay. So this is my A, this is my B. Make sense? All right. So then I need to know what my function, what is this when I graph it? It's a line. So I can use my y-intercept and whatnot, but for a line I only have to have 2 points. So if I found these two, this would probably be helpful. So if I substitute in a -6, what am I going to get? 0. Okay, so I'm here. If I substitute in 3, what am I going to get? 9/2. Okay, so we can say it's like up here. That's something like this. Okay. But we are doing this. What this means here is it's important to understand what we're seeing. This means I want to find the area between this function and the x-axis. Between this function and the x-axis. So that means this is what I'm finding the area of. This point is 3, 9/2. This is your C sub k, f of C sub k, or whatever you need there. Okay? Now, we've talked about Riemann sums. We've talked about rectangles a lot. When you know what you want, this means I want the area between this and this. So now I'm not thinking Riemann sums and stuff anymore. I can actually find that area, right? When it was a squiggly, I really couldn't. This one I can find. So even though this is a line, we talk about it as a curve, because we talk about all of them as curves. It's just a curve that doesn't curve. And we find the area. So the integral from -6 to 3 of 1/2 x plus 3 dx equals, and it equals the area of this triangle, the area concept. I'll tell you why I'm using that word after a while. So that's, how do you find the area of a triangle? 1/2 base times height. This is the base. How do I find that? What's in the middle? It is the change in numbers. Like, so what is this list? What is this distance? But subtract. You subtract b. It's really just, this is b minus a is what I need. B minus a equals 3 minus a -6. That's where we get 9 down here for this to be 9. It's b minus a. And plus you went 6 here and 3 here. Sometimes it's easy to just look at it and know, and you don't have to think about it mathematically, but you need that length. This is the base of the triangle. Now, this is a right angle because that's going to, so with a right triangle, we just have base and height, right? Base is 9, 1/2 times 9 times, what's this distance here? 9/2. 9/2. So if I think about that being over 1, that's going to give me 81 over 4. What questions you got? Make sense? So right now, so we talked about left and right hand rectangles and approximating that. We're finding exact areas now, but with things we know how to find the area of. So we're basically just making sure we know to tie it to area. All right, so let's look at number 2. I'm integrating from -3 to 3 of the absolute value of x minus 1 dx. So that means I want the area between this function and the x-axis. So I've got -3 and I've got 3. So let's think about this a couple of different ways here. Do you know what the absolute value function looks like? It looks like a v, right? So your parent function looks like this. This transformation means we did what? We went to the right one because it's inside the absolute value. So we went to the right one. Because yes, I can find these two values, but it's not in line, so I don't get to just connect them. So this point here, the vertex that was at 0, 0, went to the right one. So that's 3, 1, 2. So I've got, so that means instead of here, this is where the vertex is. Then if I find my endpoints, I'll know how to draw my V. Does that make sense to you? Okay, because you don't want to have to substitute in a bunch of, you need to know, this is why we spend so much time on parent functions and transformations. All right, if I substitute a -3 in here, -3 minus 1 is -4, but then we make it positive, so we have this point right here, this, and then 3 minus 1 is 2, and we have this point right here. So I probably should have done, see, this is my absolute value, right? And it can keep going, actually, if you want. But what I'm integrating is just this part right here. Stop me if I've lost you somewhere. Are we all good? Okay. So the integral from -3 to 3, the absolute value of x minus 1 dx equals, well, and then you just have to decide how you're going to find this area. We got 2 triangles, so I say I find 2 areas and add them together. Make sense? Okay, so I get 1/2. We'll start with the left-hand one. 1/2 times, what's this length right here? 4, because this is at 1, right? So this whole thing is 4. So 1/2 times the base, which is 4, times the height, which is 4, plus 1/2 times 2 times 2. So this is 1/2 of 16, which is 8, 1/2 of 4, which is 2, and we get 10. What questions do you have? We're all good? Okay. Let's look at number 3. Okay. So we're going to have a sketch here. I'm going from B to 5, where B is greater than or equal to 0, but less than 5. All right, and 6 minus x, what kind of thing will that graph? A line, okay? So let's put a 5 out here. And if I substitute 5 in there, what am I getting? 1. So we'll go to 1 here. What is, now I can't substitute b, and that'll be 6 minus b. I don't know what that is to get the other, but I know it's greater than or equal to 0. So I'm going to go ahead and just draw it greater than 0, just so it maybe makes a little bit more sense. So what is the y-intercept here? 6, okay? So really, that tells you two things, that it's going to go like this, plus also I should know that because it had a negative slope. So I don't even necessarily have to mark it up there at 6 because it doesn't have to be to scale. It's just going to look something like this, right? And we can make B, we'll just put B somewhere because we don't know where it is, but we know it's between 0 and 5. So that means that I want the area of this. Everybody understand how we came up with that? I could have put B on the y-axis and said it could be 0, but we'll just go with this. So I'm integrating from B to 5, 6 minus x dx, which means I need the area between this curve and the x-axis. That's why we bounded that and we shaded. What is that shape? Trapezoid, okay? So that's equal to, I know my trapezoid formula is 1/2. Then I got to add the two bases. Well, if these are my x values. Let's get these ordered pairs here. So this ordered pair would be b, comma, what? What would the y value be there? 6 minus b. This would be 5, 5, comma what? 1. And which one is base 1 and which one is base 2 doesn't matter. I usually just go left to right. So I'll use this as the first base, this is the second base. So this, what's the length of this base? 6 minus b, because it's your y value, right? So 6 minus b, and what do we do with the two bases? Add them. So 6 minus b plus what? 1, because that's the length of the other base, times the height, which is the distance between the bases. How do I find the distance between those 2 points? 5 minus b. Okay. Everybody with me so far? Okay, so for the purposes of free response, that's a safe stop. But we're going to keep going, because if it's multiple choice, you can't, maybe you can stop there, maybe not, who knows. So we're going to keep going. I'm going to put my 1/2. So since I have 6 minus b plus 1, that's really 7 minus b, right? Times 5 minus b. And maybe, if it's multiple choice, maybe that's what the answer choice looks like. Or maybe we have to keep going. I would suggest in a situation like this not to distribute that 1/2 until you're done, just because I think it's going to make everything easier. So this is equal to 1/2, and then I'm going to multiply these two binomials. So I'm going to multiply 7 times 5, that gives me 35. Then 7 times negative b, that's going to be negative 7b, and negative 5b, together to give me a negative 12b. And then negative b times negative b is b squared. That could possibly be what the multiple choice answer looks like. Or we could distribute and get 35 over 2 minus 6b plus 1/2 b squared. Maybe that's what it looks like. Or maybe they put it in standard form and you get 1/2 b squared minus 6b plus 35 over 2. If that's the case, I would think you probably would need to write that one down because you can see that. But you would want to go through these steps so that you don't make an easy, error in your brain when you're trying to match them up. Okay. What questions do we have? And so that was your safe stop, and this would be like well, really all of these would be multiple choice possibilities. Be any of them. But if you don't have to go farther, don't go farther, right? What questions you got? All right. Then I'm going to give you a minute, and I want you to sketch number 4. Okay, so it looks like we all got the first part down good, and I think some of us might be a little bit stuck. So the way I would start would be to look at, okay, so I know it's going from A to B, and A is greater than 0 but less than B. So A is somewhere here, B is somewhere here. Like, that's the best we can do, okay? Saw that everywhere. Then I need my function drawn. So we've been getting the endpoints or drawing our functions by substituting in these numbers, and sometimes we don't have numbers, but we should know what 4x looks like. What's it going to look like? A line, and what is the y-intercept? The origin, and the slope is 4, but that's really irrelevant if we're not trying to get like we just know that it's positive, so we know it's going to look like this. So we can draw this, right? And then by doing that, whatever this is bounded here. This is our region that we're looking for, okay? So very good job on that. So let's get our ordered pairs so that we can think through this correctly. This point, so I need these points because those would be the heights of, those would be the lengths of my bases, right? So this ordered pair is A, comma, what? 4A. Very good, because we substituted in here, and we get 4A. This one is B, what? 4B. And that 4B is this length because it's the y value, right? And 4A is this length because it is the y value. And we have, what is this shape? Trapezoid. So we're going to integrate from A to B, 4x dx, and that's going to equal 1/2. My first base is what? What's the 4A? Good. Plus my second base, which is 4b, times the height, which is b minus a. The height is always the distance between the bases. This is b minus a right here. Okay. Everybody okay with that? All right, so this is your safe stop answer. I want you to multiply that out on your own. You can write it the other way. I figured somebody was going to ask, which is totally fine. So yes, here I could have done 1/2 and then just leave it as negative 4a squared plus 4b squared. And then that would give you negative 2a squared plus 2b squared. Both of those, they're fine because they're the same thing, right? I was just conditioned always. That's what, old school was drilled into my brain. But again, all of this is all of these are your multiple choice. So like any of these versions could be your multiple choice answers. Sometimes they don't go all the way. They stop in the middle and just see if you can get to that point. Okay. What questions you got? Anything? All right. So then we're going to stop here for today. Monday, you have a quiz over the pink notes, area and Riemann sums. I will upload the key today, I promise, and I'm doing it in such a way when it's in a Google Drive folder, it's going to be I'm not going to upload them as separate documents anymore, and that makes everything way quicker and easier.